Welcome to the webinar, Master the Basics of Alarm Management, a review of the best practices in ISA 18.2's technical report number 3 on basic alarm design. My name is Todd Stauffer. I'm the Director of Alarm Management here at exida. I'm editor and voting member for the ISA 18.2 standard, and what's relevant for today's discussion is I was the co-chair for the development of the document that we will talk about, technical report number 3. So who is exida? If this is your first time on one of our webinars, we are a global provider of products and services in process safety, which is where we got started, cybersecurity and alarm management as well. We do certifications for products, personnel, and systems. So if you've ever put together the design of a safety instrumented system with SIL rated equipment, chances are it's exida that did the analysis to come up with what SIL rating it is. We also have a suite of tools for design and engineering of safety instrumented systems, including the support of the whole entire safety life cycle. And we include our alarm management tool called SIL Alarm as part of that. So the agenda for today's webinar, we will talk about the alarm management life cycle as defined in the standards on alarm management. We'll look at the overall suite of technical reports that were created by ISA after the ISA 18.2 standard was released. One of those is on basic alarm design. That's what we'll be looking at today. And in that, we will cover some of the best practices related to basic alarm design, particularly when it comes to the use of alarm states, selection of alarm types, application of deadband, and application of on-off delays. So alarm management, the purpose of alarm management is really to help the operator do their job, to improve operator performance. A well-designed alarm system helps the operator. A poorly designed or poorly performing alarm system actually hurts the operator, making it more difficult for them to do their job. And a poorly performing alarm system might have some of these alarm management issues. Operators might be overloaded by alarms, whether it's steady state or after an upset. You would notice this if you went into a control room after a trip of a big piece of equipment and saw that one of the operators was sitting by the console and his job was to repeatedly hit the acknowledge button to silence the horn and to scroll the alarm list. Another scenario is nuisance alarms, alarms that don't provide any value to the operator and get in the way of them doing their job. And there's different types that we will talk about. Chattering alarms, these are alarms that go in and out of alarm in a few seconds, so they don't stay in alarm for very long. Standing or stale alarms, alarms that stay on the console. A lot of times you'll walk into a control room, and if you look at the alarm list, even in a quiet mode of operation, you'll see that it's full of alarms. Those are your stale alarms. In a lot of cases, they are things like motors that aren't supposed to be working, but for some reason the alarm is set up so that when they're off, it's an alarm. So you often have a lot of alarms just because of mode-based things. So stale alarms occurring from that, and that gets in the way of the operator doing their job. There are other alarm management issues as well, but the ones that we're going to focus on in this discussion relate to what's talked about, the techniques that are talked about in this technical report, and they really have to do with addressing alarm overload, floods, and primarily nuisance alarms. And one thing I will jump ahead and tell you is that there was a study that was done by the Abnormal Situation Management Consortium in the UK primarily, that found that just by the application or the proper application of the basic alarm management techniques that we're going to talk about, it reduced the alarm load on the operator by 45 to 90%. So incredible payback could be in store. Now, I do want to focus a little bit more on what nuisance alarms are, because that's going to be one of the primary things that we are addressing via basic alarm design. And if we look at the definition, it helps understand why nuisance alarms are a problem. Nuisance alarm is an alarm that enunciates excessively, unnecessarily, or does not return to normal even after the operator takes the correct response. So that would mean the first time an alarm occurs, the operator responds, but when the alarm doesn't clear or the situation doesn't resolve itself, that leaves them wondering about the next time. So the second and third time those alarms occur, the operator may respond or may not respond, and if nothing happens, then they are conditioned to think that it's not important to respond to that alarm or it's not necessary. Now, that can become very dangerous if there becomes a culture of ignoring alarms, particularly if in a certain case, maybe the alarm that's been ignorable for months is now all of a sudden important and the operator has been conditioned to ignore it. So eliminating nuisance alarms so that operators don't develop that conditioning to ignore alarms is really important. And that's what we're going to talk about in Technical Report 3. So how does Technical Report 3 relate to the standards on alarm management? So there's two main standards on alarm management. The ISA standard, which was created in 2009, ISA 18.2, and is due for update and release. It's been finalized and approved. It's in the final formatting process and should be released any month now. And there's also an IEC international standard, which was created based on the original ISA standard, so they're very similar. Both of these standards define what's called an alarm management life cycle, which is a workflow process for alarm management. They both define the requirements of what you need to do to implement an effective alarm management system. Now, in the alarm management life cycle, we're going to focus on one of the stages, and that is the detailed design stage. Now, just to refresh what an alarm is, both standards define the definition, and that is basically an alarm. The purpose of an alarm is to notify the operator that there's a situation that requires their corrective action to prevent a consequence. We want to make sure that alarms continue to repeat that pattern and always require that response. So one of the ways that we can do that is the elimination of nuisance alarms through the techniques that we will talk about today. So when the ISA 18.2 standard was first created in 2009, after that, the ISA committee launched into the creation of technical reports. So the standard, or a standard in general, defines the requirements for what you need to do. So it defines the what, but it doesn't define the how. It doesn't tell you how to do that. That's left to the user. So one of the ways to help fill in the gap is through technical reports, which provide information on how to do things, how to comply with the standard. So it takes industry experience and best practices and documents it for people to use. And that was the purpose of these technical reports. There are 7 of them in all. TRs 3 through 6 are published and available. TR 1 and 2, I believe, have both been approved and are in their final formatting, so they're soon to be released, and TR 7 is in process. So you can see also that the technical reports go into detail about 1 or 2 stages, 1 or 2 specific stages of the alarm management lifecycle. And we're going to talk about basic alarm design, which actually I will show you now where that shows up. But first, let's look at the alarm management lifecycle overall. It starts with the alarm philosophy, which is a document that defines your guidelines and processes for doing alarm management. So it might be some guidelines related to basic alarm design. What are the recommended values to use for deadbands and on-off delays, for example? Identification is the process of coming up with a list of potential or candidate alarms. Rationalization is where you review those alarms to define which ones you need, which ones meet the criteria for being an alarm. You define their priority, their limit, their set point, document their cause, consequence, corrective action. Now, one thing I want to make you aware of is that as part of an alarm, of configuring an alarm, there are a bunch of what we would call attributes. They are parameters of the alarm. Alarm set point or alarm limit, alarm priority are examples of those. Some of those alarm attributes are defined during rationalization. Others are defined during detailed design. And detailed design is actually where we find basic alarm design. Detailed design consists of 3 different activities: basic alarm design, HMI design, and advanced alarm design. Talk about those more, all a little bit later. Implementation is where the alarm system is put into operation, includes installation and testing, configuration perhaps, operations kind of straightforward, that's the responding to alarms. Maintenance is the fixing alarms and hardware that's not working. Monitoring and assessment is the stage of the alarm management lifecycle where you measure your alarm system performance and you identify problem alarms. So this is where we would identify nuisance alarms, we would identify chattering alarms, we'd identify stale alarms that we could then go through a management of change process to fix or address or redesign. Last stage is called audit, which is where we review the processes that are being used for alarm management to make sure they match what you said you would do. So diving into detailed design, as I mentioned, it's got 3 parts to it. We're going to focus on basic alarm design, which is related to or concerned with the triggering of the alarm, so primarily related to its implementation in the control system. Second part is HMI design, or human-machine interface, the interface of the operator to the process through process graphics and displays and computer. That's concerned with the presentation of the alarm. And then the third stage is advanced alarm design, which deals with suppression, design suppression. We're going to primarily focus on basic alarm design, but we'll see some overlaps and exchanges with some of these other activities as well. So as part of basic alarm design, one of the activities is to implement the results of rationalization. It's also to continue in the definition of whatever attributes of the alarm were not defined during rationalization, and in particular those that relate to the triggering of the alarm, which could be things like alarm types, alarm deadbands, alarm on delays and off delays. And again, I'll use the word alarm attributes to describe what they are. Basic alarm design also, though, includes configuration of the logic to define when the alarm should be triggered. More on that in a little bit. So one question or one possible point of confusion would be, what is the difference between basic and advanced alarm design, and when do you follow the guidance of one technical report versus the other? So in a nutshell, basic alarm design relates to looking at individual process variables. Could be raw measurements, could be calculated variables, but it's typically related to a single process variable. And it also has to do with settings that will work for all operating states. So something that would accommodate all operating states. Maybe not very well, but that's the idea, is that there's one setting involved. They're typically considered part of the basic process control system. It also includes then anytime you create logic to make sure that the alarm only occurs when it's valid. So that's all part of the basic alarm design scope. Advanced alarm design differently relates to when you have multiple alarms that you're dealing with. So the scope is typically different, applies to multiple alarms at the same time, and it entails modifying the behavior of the alarm attributes dynamically, so for one or more process variables. The goal of advanced alarming is to make sure that those alarm attributes track the process in its different states. So it's very different from trying to set one value that will suffice for all operating states, and it includes design suppression and state-based alarming. So why would this be important, and how would it show up? One example is in the design or alarming configuration for a pump and its associated low discharge pressure. So let's say we have a pump and we have a low discharge pressure configured to indicate that there is a process supply problem. Now, as you can probably imagine, any time that the pump is shut off, whether on purpose or not on purpose, you're going to get the low discharge pressure. So those are tied together. So certainly turning off the pump, if that's intended, shouldn't result in a low discharge pressure alarm, because that's kind of consequential. So that becomes a nuisance alarm in that scenario. So how can we design the alarming for that low discharge pressure to make it more effective? If we apply advanced alarm design methodology, we would essentially suppress that low pressure alarm when the pump is not running and the pressure is low. So the alarm is actually occurring, but is being suppressed within the control system. Now you need to understand what that means, because within the HMI, that's going to have a certain presentation to the operator on the symbols on the screen. That alarm would actually appear on a suppressed alarm list, or should appear on a suppressed alarm list. And that is very different than if you had applied a basic alarm design technique, which steps back and says, let's trigger, or let's configure the logic to be smart about when it generates the alarm, and say that we're going to look not only at the value of the pressure itself to see that it's low, but we're going to also look at the run status of the pump and combine those two, and only generate the alarm when those two conditions are met, when the pump is running and the pressure is low. So what that means then is the alarm is not suppressed. It's just not going to occur unless there are two conditions that are met. So we've made the initiation of the alarm smarter. It's not suppressed. Its appearance within the HMI to the operator would be very different from the advanced alarm design methodology. So that's why that is important to understand. So if the alarm system, or if the alarm is created by the control system and logic is added to conditionally suppress it, then that's advanced alarming. So just to make sure that that's clear, the differences between those two. In general, recommendation would be to use basic alarm design techniques where possible, or when possible, before moving to advanced alarm design. So now let's look at differences between the rationalization process and basic alarm design. A complete rationalization includes a lot of steps, including determining whether the alarm is valid, documenting its consequence of inaction, what would happen if the operator doesn't respond, what the likely cause is, confirmation, corrective actions, what's the operator supposed to do, the response time. That's typically used to assess whether the alarm is valid or not. If it is, then you also define the alarm priority. Again, that's an alarm attribute. Alarm classification can be considered an attribute as well. Review the alarm limit, or the alarm set point. And then one of the final steps in the process is verifying the remainder of the alarm attributes. A pretty generic statement, but that basically means looking at things like the on-off delay or the deadband to set them as needed. So that's actually a basic alarming, or a basic alarm design step. The very final step in the rationalization process is assessing the need for special handling, meaning, does the alarm need to be suppressed or have a different limit or priority depending upon the state of the process? So that's advanced alarming. So strictly speaking, if you look at the whole set of information that you may document for an alarm during rationalization. It could include some techniques or some information that's considered part of basic alarm design and part of advanced alarm design. This doesn't mean that you can't do it as part of rationalization. It all has to do with what makes sense to you. Certainly, rationalization can be a pretty resource-intensive process where you've got operators in there and process engineers, and you might find that discussion of alarm deadbands and on-off delays doesn't really require them, which is why that those discussions were not considered to be part of the rationalization process when the ISA standard was created. It doesn't mean, though, that it can't be discussed and documented. So part of what we recommend is considering talking about that during rationalization, perhaps setting it offline. The facilitator would do that, but certainly documenting it in the same space, the same place, the same master alarm database as all of the other information. And that's what you can do with the exida SIL alarm tool. It guides you through the rationalization process as well as helps you capture and document all of the alarm attributes, whether they're considered to be part of rationalization or basic alarm design or advanced alarm design. So now let's get into TR3 and look at some of the best practices. And first we'll start with a discussion of the usage of alarm states. And when I talk about states, I mean whether an alarm is active, whether it's been acknowledged, whether it's latched, whether it's returned to normal. There's a state transition diagram defined in the ISA standard shown here. So one of the things we want to talk about then is in control systems, in many control systems, it is possible to use the alarm set point and or the alarm state, meaning whether it's active or not, as input to interlock logic. So we want to look at the design consequences of that and what that means. So for this, we'll look at an example problem where we want to implement both alarming and interlocking to prevent a tank overflow. And the design requirements are that we have an interlock that will be designed to automatically shut the feed valve when the level in the tank reaches 90%. We also want an alarm to occur when the level reaches 85%. And we need the interlock to create an alarm that will tell the operator that there are some actions that they are required to do to deal with the effects of the interlock. So in this case, it is a valid alarm. The interlock is a valid alarm because there are actions that the operator does need to take. So let's look at a couple of design implementations. The first one leverages the alarm limit and status to drive the interlock. So in this case, we have a high alarm, high level set at 85%. We have a high set at 90%. We configure the interlock logic to look at the status of the high alarm. When the high alarm goes active, we use that as the initiator to close the valve. We do not specifically alarm on the activation of the interlock. So what are the potential issues with this implementation and this use of alarm states in the design? Well, there are several. First, from a management of change point of view, the high alarm, which is set at 90%, is not only the alarm limit, it's also the trip limit effectively. So if the operator has the ability to change that alarm set point from the operator interface, from a faceplate, for example, they would effectively be changing the trip point of an interlock, which could be quite dangerous. And they may not even know that that's what they're doing because it's not well defined or documented or represented. Also, if the alarm would be disabled or suppressed, that would prevent the activation of the alarm, and then the interlock would never activate itself. So that would effectively defeat or bypass the interlock from happening. The other problem with this implementation is that the high alarm doesn't actually indicate that the interlock is activated. We don't really know whether that has happened because that's downstream logic that we're not looking at in the way this is configured. So we don't really truly know the status of the interlock. So hopefully based on this discussion, you're thinking that, gosh, this is not the ideal way to do things. And in general, this is not the recommended way to do things because all of these potential issues can compromise the integrity of the interlock such that it may not activate when it's required. So depending upon the importance of the interlock, you might want to think about redesigning if you've done it this way. Or make sure that you have rigorous management of change processes in place to make sure that items like changing the limit or disabling the alarm cannot happen. So that would be what you would need to do to make that a viable technique. Now what's recommended is instead to create the interlock logic by comparing the actual process variable, the level, to a hard-coded trip point, the 90% trip point, hard code that in logic and use that to generate the interlock. And then once the interlock is activated, once that's gone through, use that to create the interlock activation alarm. We can set the alarm at the high alarm at 85%, and then we can even define another alarm, a bonus, a high alarm at 95%. That would let us know if for some reason the interlock did not work or did not activate. That would be an indication of that. So what's different or what's better about this implementation? It does not have the design issues that the previous design did. It also allows you to optimize the alarm settings, what the alarm set points are, totally independently of the trip point. So it maintains the interlock integrity while allowing you to adjust the alarm set points. So in this case, the likelihood that that interlock would activate as required or upon demand is much greater than design number one. Another area that's covered in the technical report relates to re-alarming alarms. Now, if you've listened to any of the other alarm management webinars, you might think, what are we talking about? The idea of re-enunciating an alarm that has already been presented or is not cleared to draw the operator's attention to it seems counter to everything that we talk about related to the importance of an alarm and the operator responding to it the first time it occurs. And that is true. And that is why this is not a recommended approach. This is a practice that in general should be avoided. Why? Well, hopefully it's kind of obvious, but certainly it adds load to the operator, so they're getting more alarms. Part of what we were trying to do previously as part of alarm management was to reduce the alarm load on the operator. Well, using re-alarming alarms is only going to increase it. It's also going to have a nuisance alarm effect, and it's going to condition the operator that they don't need to respond to the alarm the first time it goes off, because there's going to be a second time. So that's almost the same kind of thought pattern that goes with nuisance alarms. So that's something we definitely want to avoid in general. So it's not a recommended approach except in rare and specific cases. And what is recommended by the committee and the team that worked on it is, in general, you do not use this, but if you find that there are certain scenarios that require it, that's when you implement it. So what are some examples? Well, you might have a case where an alarm occurs, it is not cleared or not corrected, and now the consequences have gotten significantly worse. So now you may want a worse to the degree that the priority of the alarm is actually escalated. So now you may want to re-enunciate that alarm to say, hey, this alarm is still active, and guess what? It's getting worse pretty quick. So that's one scenario. Another scenario is when the process response time is quite long, say on the order of several hours, where the time from when the operator initially responds to when the process should correct itself is quite long. That's when re-enunciation or re-alarming might also be helpful. And then for a very select group of critical alarms, you may want to re-enunciate those alarms at the beginning of a shift. So when a new operator comes on, for example, any highly managed alarms, or safety critical or safety related alarms, you may want to re-enunciate them so that they are back at the top of the screen. The operator has to acknowledge them. They need to respond. They need to investigate. It's right in the front of their mind, which is very different from if the alarm is active and buried on the screen somewhere. So that's the other scenario where it may be useful to use this technique. Another area that the technical report goes into in great detail is a discussion of alarm types and when to use them. When is the best scenario? What are the pros and cons or the guidelines associated with the use of high and low alarms versus deviation alarms and rate of change? And in general, the recommendation is there are a lot of different alarm types that could be used to generate an alarm. You want to pick for indicating that abnormal condition that you're trying to get the operator to respond to. And low alarm, that may be 95% of the alarms that are best alarm to a reactor. We need to make sure that it doesn't exceed the target by more than 10 gallons per minute. Now we have different targets for flow rate depending upon the production capacity or what production we're running. If it's at full rate, the target flow rate is 120 gallons per minute. If we're at half rate, it's 70 gallons per minute. So the question is, what alarm types and set points should be applied in this scenario? If we factor in the targets, we know that we'll need an alarm to prevent the flow rate from going above 130 gallons per minute for the full rate scenario. And for the half production rate scenario, we'll need something that prevents the flow from getting above 80 gallons per minute. So what would be the best scenario? We could implement a high alarm at 130 gallons per minute. That would certainly work well for the full production rate scenario, but it wouldn't work very well for the half rate scenario. In fact, it wouldn't really work at all. It wouldn't be effective at all in that scenario. So that's only going to work part of the time. We could take that high alarm and build in some logic that would change the limit or have the operator change the limit depending upon what production rate we're running. But of course, that's significantly more complicated then, and that's actually an advanced alarming technique. The last option is to implement a deviation alarm where the limit is set to 10 gallons per minute. That's actually the optimum selection in this case. Because if you think about what you're looking to try and do, it's to make sure that the flow controller is doing its job. You're not really concerned about the absolute magnitude of the flow. So really a high level and a high alarm is not ideally what you're after. What you're after really is a deviation to indicate that you're going away from the target of your flow controller and your flow controller is not working. So implementation of a deviation alarm here actually meets all the design requirements in a way that's better than if you used a high alarm in either of the scenarios. So put some thought into selecting the best alarm type. As I mentioned, the technical report does go into a lot of detail about things to consider for different types of alarms. For example, with deviation alarms, making sure that you're using them at the right time, that you're considering the fact that They can be nuisance alarm generators, particularly under transient conditions, changes in the plant operating conditions. So the recommendation is really to not implement deviation alarms across the board, but really only when they're needed or when they're the best or appropriate alarm type to use. So look for guidelines or guidance similar to that. We've also gotten information on implementation of instrument diagnostic alarms, such as bad PV alarms. These can be some of the worst sources of nuisance alarms to an operator. So it's worthwhile thinking about how you're going to address these alarms. Are you going to present them all to the operator? Do you want to have this alarm enabled for every analog point? What if you have an analog point that doesn't have any other alarms? Do you need to have the bad PV alarm? How do you set the priority of the bad PV alarm, maybe in relation to the other alarms from that tag? So there's a lot of things to think about or to consider when it comes to implementing bad PV alarms or instrument diagnostic alarms. So the document gives some guidance that can be applied to hopefully help you optimize the way you're doing it. It also talks about another scenario is common alarms. So scenarios where you have multiple sensors creating alarms where you realize that you don't need to individually alarm or enunciate every single one because the operator's action is the same to each one. The priority of the alarm is the same to each one. So you can group them together in a common alarm. Defines guidelines for that, for the practices that you should use, including, as I said, making sure that the priority is the same of all those underlying conditions and that the operator response is the same. So if you think about a check engine light in your car, that's a common alarm, but it actually violates most of the recommendations in the document, because in my car, for example, a check engine light could come on to indicate that it's time to make the appointment to get the oil changed. It could also come on to indicate that my fan belt has just busted and I'm going to be stuck on the side of the road in 200 yards. Obviously, my response to those two scenarios is going to be very different. So that would be not a good example of a common alarm. So now moving on to the next topic, and that has to do with how to eliminate chattering alarms or a type of nuisance alarm through the application of deadbands and on-off delays. And there's a lot of guidance and guidelines and information and examples in the technical report about this. So alarm deadband, or hysteresis as it's called in some control systems, is a way to make sure that an alarm actually only occurs once, or to reduce the amount of times that an alarm actually occurs. If you look in this scenario to the left, we have a noisy process variable. It's certainly increasing generally, going above its alarm threshold, so we do have a legitimate alarm case, but just because of the noise and it clearing and going up and above and through the limit, we actually end up with 4 alarm enunciation events for one condition. So that's a nuisance alarm. That's actually a chattering alarm. To the operator, that could be quite annoying. They may ignore the alarm. Hopefully they won't, because they'll realize it's valid, but it will still be annoying because the alarm is occurring 4 times. The purpose of deadband then is to put a buffer that smooths out that fluctuation so that the normal fluctuation in the process variable doesn't cause alarm events just because of the fluctuation. So in this case, unless there's a significant enough change in the process variable, once the alarm has occurred, it's not going to clear unless it drops down below not only the limit, but through the deadband as well. That's how deadband actually eliminates chattering alarms. Now, when it comes to setting deadband, there's a couple of different recommendations or a couple of different practices. One is doing it based on the type of process variable and the range. So if it's a flow, one recommendation is to use 5%. Now these guidelines they've been around for quite a long time, even before AMUA 191. That's where they first appeared. So some people look at this as a maximum to be used on a case-by-case basis, maybe a starting point, but certainly not to be applied blindly. When it comes to deadband in general, you want to apply a factor, monitor the results and the operating results, and adjust as necessary. So certainly review based on your operating experience. So let's look at how, if we apply deadband based on the range, how that would actually work. So here we have a pressure gauge that's scaled from 0 to 100 psig. We have a high alarm configured at 90 and a deadband at 2%. So that means that when the pressure goes above 90, it'll be an alarm, and any fluctuations between 88 and 90 won't cause the alarm to clear or to create any new events, and the alarm won't actually clear until it gets down below 88. So again, that's how we would eliminate chattering alarms. Now let's look at that same scenario, but a little bit different of a control strategy. A 10% deadband and a pressure regulator thrown in there that prevents the pressure from going below 85 psig. So in this case, again, high alarm limit at 90. The value of pressure goes above 90, the alarm is triggered. Any fluctuations between 90 and 80 won't clear. And now we need for the pressure to go below 80 for the alarm to clear. The problem is, in this case, that we have a pressure regulator that will actually prevent the pressure from getting below 85. So once that alarm occurs, because of the deadband choice, the alarm will never clear. So we have created a stale alarm because of the misapplication of deadband in this case, and poor understanding of the process design. Now I mentioned that one of the ways to apply deadband is based on your range. I didn't really talk about what I meant by range, and that can be kind of confusing, and it's important to understand exactly what we mean, because there are different ranges within this scheme of a control system. We've got the instrument range. That's more like the capability that the instrument might have, let's say 0 to 500 psig. Then there's the calibrated range, which represents the range that's being used in a certain application. So the settings that correspond to 4 to 20 milliamps, in this case 0 to 100 psig. And then the configured range within the control system, within the DCS configuration and control itself. In this case, we're assuming that that's the same as the calibrated range. But in this case, it would be 0 to 100 psig. That's what should be used for the application of deadband, the configured range. So when we say 2%, it should be 2% of your configured range, generally speaking. But you still need to understand the application, and depending upon the operating range, you may need to adjust. Here's an example. Let's say we have a flow transmitter whose range is 0 to 100,000 gallons per minute, and because it's a flow, we're going to apply a deadband of 5% to that 100,000 range. But we have a high alarm that's configured at 10,000, and the configuration range in the DCS is 0 to 15,000. So if we apply the 5% deadband against the full instrument range of 100,000, we actually end up with a situation where we're going to create a stale alarm. The alarm would actually trigger when it gets above 10,000, and then would not clear until it drops below 5,000. So in this case, Here's an example of when we misapply deadband by not understanding the right range to apply it to. We can end up with a stale alarm or creating an alarm issue that we didn't have before. Another way to define deadband or set deadband is by looking at the signal noise itself. If you can measure that, if you can look at the fluctuation in the process variable during steady state or quiet conditions, you can set the deadband in relation to that. We want the deadband to be slightly bigger than the noise. Typically set to 2 sigma of the noise distribution is what's recommended. But the general idea is if you can see what that fluctuation is, you know where to set the deadband to make sure you've got it covered. So an example of setting deadband based on evaluating the signal to noise ratio, the noise itself, versus the recommendation based on it being a flow or a level. And in this case, choosing to use the noise as the guiding factor and implementing a 10% deadband. Now, one of the reasons why deadband is important is because of how it affects the operator in the behavior of alarms. Here's an example of an alarm summary display from Honeywell system that shows a whole bunch of information about the alarms, priority, tag, and including what is the alarm limit and what is the current value of the alarm. So here's where deadband shows up, because if we were looking at a high alarm, we could find that the current value drops below the alarm limit and doesn't clear, and it's still on the board. It's still showing. That could become confusing to an operator who doesn't realize that there's a deadband or a significant deadband applied. So they might not understand why that is. I also found some operators recently that were telling me they use deadband or they change the deadband to 0 in cases like that to get rid of those alarms, because those alarms become stale alarms. As soon as the actual value goes below the limit, you'd like to potentially see that alarm clear. Depending upon where that deadband is set, that alarm could still remain on the board for quite a long time. So this set of operators would actually go in, temporarily set the deadband to 0, which would cause the alarm to clear, and then they would set the deadband back to its original value to help clear the situation up. Now, probably they would have done better if they had just looked at maybe modifying what those default deadbands were, maybe by looking at the signal noise and setting it in relation to that. In addition to deadbands, there's also parameters called on delays and off delays, which relate to delaying the enunciation of the alarm to the operator for a certain period of time to make sure that the alarm stays true or the condition stays true. And the reverse of that is the off delay, and that's the delay of the clearing of the alarm. So that can also be used to eliminate chattering alarms. And there are recommendations, again, published in the ISA standard about some default or recommended on delays and off delays. These values I would certainly only use in scenarios that this is required. Typically what I see is most alarm philosophy documents, these on delays and off delays are set to 0 unless required by the situation. So now let's look at all those techniques together and talk about how they work and which ones we do first. So we've collected the best practices of the working group committee and documented that in the technical report, and here's a summary of that. So in general, you should apply alarm deadband first. That is the most powerful of those 3 techniques. If you find that that is not sufficient or is not available, then you would use on delay, which is the second most powerful, typically followed by off delay as necessary. Now, when it comes to use of on delay, that deals with chattering and fleeting alarms, but you have to be careful because you are delaying the enunciation of the alarm to the operator. So if you were, for example, to implement a 60-second on delay with an alarm where the operator only has 5 minutes total to respond, that might be a problem. So some people shy away from the use of on delay because of that. Off delay is not near as powerful, but it doesn't have near the potential downside. It's just delaying the clearing of the alarm. So those are the recommendations on how to use them together. And as I mentioned earlier at the start of this, the ASM Consortium study found that application of deadbands and on-off delays based on, for example, the guidelines in this technical report, when they did the study and measured the results, they found that it reduced the actual alarm load on the operators by 45 to 90%. So not small potatoes. Another thing that's quite interesting is if you look at the IEC version of the alarm management standard, that's the international version. There are actually requirements in there related to control systems providing the ability to implement deadband and on-off delay. So that means going forward, if you're a control system supplier, this is a requirement to have in your alarm system. Now, why would that be in the standard? Well, that's because folks recognized how important or how integral these tools can be as an easy way to reduce the alarm load and clean up nuisance alarms. So that's actually a requirement for control systems to have going forward. Now, another thing that the technical report has, I believe this is the last topic here, is some guidelines on the messages that get presented to the operator, making sure that they have a consistent structure, using and where using abbreviations in particular, certainly making sure that you're referencing a site library. If you've ever looked at a system where you had more than one engineer, let's say 3 engineers have done the configuration, you'll probably find 4 or 5 different ways to abbreviate a certain term like reactor. And that can be incredibly confusing to the operators, particularly newer operators or operators that are transitioning from one unit to another. So it's definitely something to try to clean up during rationalization or during basic alarm design, and to make sure that you're using or defining some acceptable abbreviations, and then either using that abbreviation or the full text string. That's the recommendation. So now, kind of reaching the end of our discussion here and looking at some of the key takeaways. Hopefully you've seen that the proper application of basic alarm design techniques, particularly deadband and on delay and off delay, can eliminate some of the most vexing alarm management issues like nuisance alarms. We can eliminate stale alarms. We can eliminate chattering alarms through that, thus making the alarm system a more viable tool for the operator to use. We also saw that if you don't implement these techniques correctly, such as if we put in a deadband that's too large, that can create new problems. It can create stale alarms, for example, where one didn't exist before. Also want to make sure that that you're thinking about applying these techniques not just to process alarms, but also to your diagnostic alarms as well. As I mentioned earlier, sometimes those can be some of the worst nuisance alarms to the operator. And implementing on delays and off delays for those might be the key to making the operator's life a lot more bearable. And as I mentioned also, support for on delay and off delay and deadband may actually vary depending upon the type of control system. But going forward, it's actually a requirement in the international version of the alarm management standard that control systems provide that capability going forward. So at this point, I will say thank you very much for listening and for attending. I have a short listing here of some of the other alarm management webinars that have been recorded and are on our website. Feel free to check them out if you haven't listened to them previously. And if you have any questions or feedback on this presentation, certainly shoot me an email at tstauffer@exida.com. I'd also encourage you to check out the actual technical reports, Technical Report 3 and the others that are available from ISA. They have a lot of good practical guidelines and information in there to help you conform to the ISA standard and implement an effective alarm management program. So with that, I will potentially close it out. I'll quickly look to see whether there's any questions. These actually look like some good questions that are going to take a couple minutes to answer. So I think what I'll do is I will answer them in an email and send them all out to folks to take a look at. So again, I'll say thank you for attending, and I encourage you to attend future exida webinars.